What's up, boys and girls and everyone else? This is another science video lesson episode in chemistry for you. And for this episode, we will be going to talk about the culmination of all the gas properties and combining them into one distinct equation that will describe the behavior of gases. Come join me today as we discover these concepts and find out what is the ideal gas law. Alright, so here we are in our topic for this video lesson, the ideal gas law. But before we go to this one, special shout out to my grade 10 students who are currently watching this video lesson right now. So, patience is a virtue, guys. So, if you want to learn something from this video lesson, so patience is required. Alright, so good luck, everyone. So, what do we mean by ideal? What do we mean by the word ideal? Alright, so first one, the opposite of ideal is real. Okay? So the opposite of that is real. So what do we mean by the word ideal? So ideal is synonymous to the word perfect, something like that. And it is somehow connected to satisfying one's conception of what is perfect, what perfect is all about. Okay? For example, if someone will ask you what is your ideal girl or ideal man, okay, or ideal guy, something like that, you will cite some preferences which for you think that is perfect. Okay, but in reality, there's no person like that. Okay, but in this world, just remember, in this world there's nothing perfect. Okay, something like that. So you will cite some preference about something that is a perfect quality for a perfect girl or perfect man, something like that. But the thing there is, fate will give you something which is real. Okay, so why do we need to have some ideal preferences? One is for motivation, okay? To give ourselves motivation to do something, okay? To do something and something to look forward to, okay? So that is what, that's the reason why we cite some preferences of some qualities that for us that is perfect, okay? Now, since we are talking about what is the word ideal, so if we will put this one in chemistry, so what do we mean by ideal gas law? Alright, so these are said to be assumptions. Okay, these are said to be sets of assumptions that talks about the behavior of these gas molecules. Alright, so without further ado, let's jump right into it. Alright, so in the ideal gas law, so this is the formula for the ideal gas law. So we have the PV and RT. Alright, so as you can see here, you can see all the measurable properties that we have encountered in the previous gas law. Now, if you don't know or if you don't have any idea what are these previous gas law that I'm talking about right here, just click the link above. It will display there. Just click that link and it will lead you to each and every gas law that we have encountered before we get into this. Alright, so we have here the PV and RT. So do you see the Boyle's law in this equation? Yes, there's the Boyle's law here. So we have here the PV that shows the Boyle's law. Do you see the Charles law? Of course, there's a Charles law. So this is the relationship between volume and temperature over there. Alright, all you need to do is to rearrange them properly. And also, do you see the Gay-Lussac's law? Okay, do you see the Gay-Lussac's law? So definitely, you can see the Gay-Lussac's law. That is the pressure and the temperature over there. Okay, and we have the combined gas law. Do you see the combined gas law in this equation? So of course, there is. So we have the PV over here, and it is directly proportional to Alright, so it is directly proportional to the temperature that you have right there. And finally, we have the Avogadro's law. Alright, so the Avogadro's law, we have the volume and the number of moles over there. Okay, so meaning to say, the ideal gas law is the complete package. Alright, so it is a complete package that explains all the gas law that we have encountered beforehand. Okay, so this particular idea brings together all these measurable gas property from pressure, volume, number of moles, and temperature. The ideal gas law brings them together. Alright, so, and the ideal gas law can be derived from experiment and theoretical ideas. Okay, so this is where the ideal gas law came from. Okay, so let's discover more. What is this ideal gas law here? Alright, so ideal gas law is somehow interconnected with the kinetic molecular theory. Alright, so it is connected to the kinetic molecular theory. Now, in the kinetic molecular theory, there are set of assumptions. There are some assumptions that explains why gases behave the way they did. Okay? So, that makes them ideal. Alright, so that makes them ideal. So, number one, okay, if you recall this one, so if you don't have any idea about what is kinetic molecular theory, just click the link above. The link for the measurable properties of gas. I have a video on that, so you might want to watch it first beforehand. Okay, before we have this, before you go deeper on this topic. Okay, so the first assumption that we have here in the kinetic molecular theory is, number one, gases are so small that they assume to have zero volume. Alright, so the second one, they are constant, they are in constant, the molecules are in constant straight line motion. Number three, gas molecules experience elastic collision. Alright, so that is why no energy is lost. Okay, according to this assumption that there is no attractive or repulsive force towards each other. Okay, there is no attractive or repulsive force towards each other. And the fourth one is the average kinetic energy is directly proportional to the temperature. Alright, so the movement of molecules, the faster the movement of the molecules, it tells us that the temperature is increasing. Okay, so that is the fourth assumption. Okay, so these things that you have right here, these four assumptions that you have, tells us, alright, it tells us that these gas particles behave ideally. Okay, so these gas particles behave ideally. That's the reason why we created these gas laws beforehand. The Boyle's law, Charles' law, Gay-Lussac, combined, and Avogadro's law. They are formulated because we assume that this particular set of assumptions that you have right here is simplifying or talks about the behavior of these gas particles. Okay, so specifically, if we will going to condense them to condense those properties or those assumptions, okay, technically speaking, there are two properties. Number one, ideal gas particles are treated as dimensionless point. What do you mean by this? All right. What do you mean by this dimensionless point? So, what particular measurable properties are we talking about when we meant by dimensionless point? Okay? So, this is the volume. Okay? So, this is the volume. Since gases are very small, alright? When you put gas molecules in a container, since they are very small, okay, we tend to assume that they are dimensionless. Okay? We tend to assume that they are dimensionless, but in some cases gases have dimension. Although it is very small, but with certain conditions, we can find out the dimension of these gas molecules. Alright, so we will try to find it out later. What are those? The second assumption that we have right here, based on the kinetic molecular theory, is that ideal gas particles do not interact with each other. Alright, so they do not interact with each other. Okay, but there are some conditions where gases tend to interact with each other, especially electrostatic force. Alright, this electrostatic interaction, the gas particles tend to do that one, especially those particles that has a polar in nature or non-polar in nature. Alright, so they tend to attract or repel as long that a certain condition is achieved. Okay, so that's the second one. Again, we will talk about that one later. But for now, the reason why gases behave ideally, it's because of these two properties that we have right here, right? And in reality, there are no gases that fits this definition perfectly. Okay? As I've said earlier, what do we mean by the word ideal? This is one conception of what is perfection all about. But in reality, gases are not perfect. Okay? Now, why do we need to assume? Okay? If you may ask, why do we need to assume? It's because of one thing. We need to simplify our calculations. That is why we tend to use this formula that we have right here. This simple formula. Now, the simple formula that you have right here is product of assumptions, alright? Assumptions that these properties is somehow existing on your gas particles. Okay? So, this is the ideal gas and then the kinetic molecular theory. Alright, so in the ideal gas equation that I've shown you a while ago, there are some relationships that we might that we encountered. Alright, so the first one is the relationship between pressure and the number of moles. Alright, so this is the pressure and the number of moles. So what is the relationship between the two? So that is directly proportional. So does it make sense? Yes, because there's no such balloon when you try to exhale inside, or when you try to inflate the balloon. Alright? You try to blow air inside the balloon several times in order to inflate it. Now, by doing so, you increase the number of moles. Okay? By doing so, you increase the number of moles of air inside the balloon. Upon doing that, the pressure also inside the balloon increases. Okay? So, as the number of moles increases, the pressure inside the balloon also increases. So, therefore, the relationship between these two are directly proportional. Alright, more so, we have the pressure and temperature. So, this is the Gay-Lussac's law. Okay? Now, one of the very good example of this is, okay, the warning on the spray can. Okay, if you read the warning on the spray can, do not throw the spray can on fire. Okay, so do not throw the spray can on fire. Why? It's because of one thing. It will explode. As the temperature of the spray can increases, the pressure of that spray can increases as well. Okay, so that is directly proportional. Okay, so that is the P and the temperature and the pressure relationship. And finally, we have here the Boyle's law. Alright, so if you are familiar with this one, the Boyle's law. Okay, so Boyle's law talks about that pressure is inversely proportional to volume. Alright, so pressure is inversely proportional to volume. Now, when you have a balloon, when you have an inflated balloon and you try to squeeze that balloon, what do you think will happen? It will explode because the pressure inside the balloon is being, if you increase the pressure inside the balloon, the volume of it will decrease. But the pressure you applied on the balloon will also, the volume will decrease, but the pressure that you apply in order for that volume to decrease is greater. Alright? So, therefore, that is inversely proportional. So, when you do that, the balloon will explode. Okay? So, when you squeeze that inflated balloon. Okay? So, that is one good example about this relationship that we have right here. Again, this is an inverse proportion that tells us that pressure is inversely proportional to volume. Alright? So, with that, combining them all together, we get the equation that we have in the first place. Okay, so this is the ideal gas equation. Okay, so the proportionality that we are talking about earlier, this is the R. All right, so if you may ask, what is this R? Okay, so we have the pressure for P, volume for V. The small n is for the number of moles or the amount of gas, and the temperature is for the T. Alright, so what is the R? R is the universal gas constant. Okay? Now, there is such value on that constant. So we have 0.0821 atmosphere liter per mole Kelvin. Alright. Now, if you change the unit for pressure, you will get, for example, I've used, instead of using atmosphere, I am going to use kilopascal. Alright. So, the value is completely different. But, the value or the numbers is completely different. But, the thing there is, it's still the same. It's the same R. Okay? So, I just changed the unit of the pressure from atmosphere to kilopascal. So, it will have 8.314 kilopascal liters per mole Kelvin. Now, I know what you are thinking. Right? So, I know what you are thinking. If you change this one to millimeters of mercury, it will have different value. Yes, you are correct. Okay? You are correct on that. If you change this one into millimeters of mercury or torr, or even in Pascal, alright, if you change this one into different units, this value will also be different as well. But, they are the same R at the end of the day. Okay, so, how did we get this R? That's the question. How did we get this one? Okay, so I have this sample problem over here. R is known as the universal gas constant. Now, the question is, how did we get this one? Okay, now, we got this R value using the STP conditions. Okay, so we use the R value using the STP conditions. So I know you are familiar with those STP. We have encountered that one several times on the previous video about the gas laws. Alright, so what are the STP conditions? The first one is the pressure. The STP for pressure is 1 atmosphere. Now, if you will change this atmosphere into kilopascal, so that is 101.325 kilopascal. Alright? Now, if you will change the atmosphere into millimeters of mercury, that can be 760 millimeters of mercury. Okay, now if you want to change it into Pascal, so that will be 101,325 Pascal. Okay, so any of these units can be plugged in here as long that that is STP. Okay, as long that it is STP. Next one, the volume is at STP, the molar volume is 22.41. Okay, so we have encountered that one in the Avogadro's law. Okay, so the next one is the mole over here. Okay, so the mole over here, and it talks about the 1 mole. Okay, the 1 mole. 1 mole of any gas, alright? 1 mole of any gas is equal to its molar mass. If it is a molecule, that is the molar mass. If it is an elemental gas, like, xenon, neon, okay, helium, something like that, it is equivalent to its atomic mass. Alright? It is equivalent to its atomic mass. So, that is the 1 mole. Alright? So, again, 1 mole, if it is a molecule, it is equivalent to molar mass. If it is an elemental gas, like neon, xenon, and krypton, etc., etc., that is equivalent to the atomic mass. That 1 mole is equivalent to the atomic mass. Now, and also, the absolute temperature, which is always in Kelvin. Always take note that is always in Kelvin, not degrees Celsius, not degrees Fahrenheit. Now, this one is equivalent to 0 degrees Celsius, if you may ask. So, that's the standard temperature and pressure, the 0 degrees Celsius. Now, if you will use this formula in getting the R, okay, so if you will use this formula in getting the R, you will get this value. So, familiar with this value? You have seen this one a while ago. Alright, so you have seen this one a while ago over here. So, that's how you get this value that you have. Okay? Now, if you are not satisfied, you might want to try using this instead of 1 atmosphere. Then, try to find out if you can arrive with the same, if you will arrive with the same value that we have over here. Alright, so also you can use millimeters of mercury and see what is the value for that one. Okay, so that's the R. Alright, so we have here a sample problem related to the ideal gas law. Now, in this sample problem, the purpose of this is to show you how the ideal gas law formula works and what are the things that you might encounter. Okay, so you may answer this one beforehand, so you can pause this video and try to answer this problem. Now, don't worry if you have an incorrect answer. Okay, if you have an incorrect answer, let me know in the comment section. Alright, later, as I reveal the answer, let me know in the comment section what are the things that you missed out. Okay, what are the things that you missed out that leads you to the incorrect answer. Alright, so you can pause this video, alright, if you want to. Okay, so the problem was, what is the volume that 500 grams of iodine will occupy under the conditions of 300 degrees Celsius as temperature and pressure of 740 millimeters of mercury. Alright, so the first thing that you will do probably is to write all the given variables. Alright, so we have the mass, the temperature, the pressure, and the R. Don't forget this one. Alright, next one, you will use the equation, this one, and since we are looking for volume as the problem is stated, okay, so you can use, or you can we can derive this formula, right? Okay, so we can derive this formula, and upon putting all the variables that you have right there, you will lead up to wrong answer. Okay, now if you put all the variables, as is, like the one that you have over here, if you put all the variables as is, then your answer will be incorrect. Okay, so your answer will be incorrect. Now, the thing here is, what are you going to do before you solve? Okay, what are you going to do before you solve? So these are the things. The first one is, if the given is in grams, alright, if the given is in grams, so the question is, what will be your N? Okay, if the given is in grams, so don't panic, right? So don't panic. You still have your N. All you need to do here is to convert that mass into moles. Okay, if it is in moles, you can convert that one into mass. Alright, so in our case, we have 500 grams of iodine. Alright, so this is a gas. Okay, now always remember that iodine exists in diatomic forms. Not only iodine, but also fluorine, alright, bromine, chlorine, alright. So those are elements that exist in diatomic forms. Also, we have nitrogen, we have oxygen, and we have hydrogen. All these elements in gas form, exist in diatomic forms, except for noble gases. Okay? Except for the noble gases, they do not exist in diatomic forms, like helium, xenon, radon, argon, krypton, something like that. They do not exist in diatomic form. All right. So what are we going to do here? We will convert 500 grams of iodine to number of moles. So what are we going to do on that? So we have 500 grams of iodine. Don't forget diatomic, and we have the molar mass of iodine. All right, we have the molar mass of iodine. So if we will going to take a look on our periodic table, okay. So the iodine is 126.90. Okay, so 126.90 times 2. Okay, 126.90 times 2, you will get 254. Okay, an estimated of 254. So that's the thing there. Okay, so 126.90 times 2, that is 254. So doing so this will be the molar mass of I2. Alright, so this will be the molar mass of I2. Then dividing 500 grams to 254, cancel the grams, you will get this value. Okay, so we will get that value. So that's the number of moles. So we have now an N. Okay, how about the temperature? Don't forget the temperature, the SI unit for temperature for the ideal gas law is Kelvin. Alright, so the SI unit is Kelvin. So, 300 plus 273.15. Okay, if you will add the 0.15, you will get 573 Kelvin. Alright, so you will have 573 Kelvin. Okay, next one. Don't forget also to convert your pressure. Okay, if you may ask, okay, can we use this one for our computation? Yes, you can use this one. You can use this unit, but make sure that your R also has that unit. Okay, do you get the point? Alright, so again, can we use this one? Yes, as long that the R has that same unit. If it is not, okay, if it is not the same unit, then therefore you need to convert this one to atmosphere. Now, upon doing so, I taught you already in the previous video lesson on how to do that one. So, if you convert this millimeters of mercury to atmosphere, you will get this value. Okay, so you will get this value. Okay, so that is 740 divided by 760. So you will get this value that we have right here. Now that everything is complete, so atmosphere, that is good to go. Okay, now that everything is prepared and everything is complete, we can now compute. Using the same formula that we had earlier, we can write now all the given data. Okay, and their converted forms. Okay, so we did conversion on this one. We did already the conversion on this one, and the same formula, the same derivation that we have over here. Now let's plug in all our values. Okay, so let's plug in all our values over here. So we have this one, this number of moles. Okay, so we have this one. Okay, the R over here, the N, the R, the T. As you can see, the T is in Kelvin, or the temperature is in Kelvin, and we have the... Okay, now the reason why it is atmosphere, it's because of this. You will cancel this, cancel that, cancel the Kelvin over here, and cancel the atmosphere. Now, imagine if this one is in mercury, millimeters of mercury. Imagine if this one is mmHg, or millimeters in mercury. Can you cancel the atmosphere and millimeters of mercury? Can you cancel the two of them? No. Okay? Only by having the same unit, you can cancel that unit. Okay? So always remember that one. Alright. Now, upon doing so, we can get this particular answer. Now, I have the habit of completing the answer. Alright, I have the habit of having the final answer in a complete form. So 95.1 liters of iodine is the new volume that it will occupy. Alright, so although it is very tasking to do, to have a final complete answer, but it pays a lot. Okay, it pays a lot to have a final complete answer. So the final complete answer for this problem that you have right here is 95.1 liters of iodine is the new volume that it will occupy. Alright, so that was the problem, and I hope you be able to see your mistakes. On this problem that we have right here, so that in the next sample problems that we will encounter, you will apply those learnings in order to solve the ideal gas law word problems. All right, so that is the sample problem for the ideal gas law. All right, so here we are now to the part where we compare. Okay? As we all know, the opposite of ideal is real. Okay? The opposite of ideal is real. Now, the question is, what is real gases? Okay? What is this real gases? Does it follow the ideal gas law that we have a while ago? Alright, so that is this part all about. Okay, that is what this part is all about. Okay, so we will try to find out what is the differences between, or what are the differences between ideal gas and real gases. Alright, so first things first, is the real gas following the PV and RT? Okay, that's the question. The ideal gas, of course, it is. That is the ideal gas. Okay, right? So this formula right here is the ideal gas. So that is why it follows. Okay? That's the ideal gas. But the real gas only follows this if the temperature is low, or the pressure is low and the temperature is high. So I repeat, the real gas only follows this formula if the pressure is low and the temperature is high. So in short, there's something going on when the pressure is high and the temperature is low. Alright, so there's something going on with the real gas if that's the case. So the second one is the molecular volume. The ideal gas, as the kinetic molecular theory states, it is zero. Alright? It is zero. But in real gases, as long that there is a condition, as long that the conditions are met, real gas doesn't have a zero volume. Alright? I repeat, the real gas doesn't have a zero volume. It is very small, but it is non-zero. Alright? It is very small, but it is non-zero. That's the point there. Alright. Next one. How about the interaction? Alright. How about the electrostatic? So this is attraction and repulsion. It talks about the electrostatic interaction between molecules of gases. Now, in ideal gas, since the gas molecules are doing elastic collisions and no energy is lost in the process, since they are doing elastic collisions, then therefore, these attractions that you have right here that is done by electrostatic concept, okay, these attractions and repulsions between gas molecules is negligible. Okay? But in real gases, if the conditions are met perfectly, you may not have a zero interactive forces. Okay? You may not have a zero interactive forces. Instead, you have a small interactive forces. Okay? The point here is, although it is non-zero, alright? Although it is non-zero, it still have a value, but it is generally small. Okay? It is basically small. Okay? But it is non-zero. Alright, if the conditions are met. Now, what are these conditions? Okay, if you may ask, what are these conditions? So the first one that we were going to have here is, I will show you a simulation that will showcase these conditions. Alright, so let's go into it. Alright, so this is the simulation. Now, the simulation that I'm using right here is courtesy of PET Simulation. So you may go to their website. The website is on the description below. There are a lot of simulations that PET Interactive offers. Okay? From general science to biology, chemistry, earth science, physics, and even math. Alright? There is. Alright? So just go to their website. The website link is on the description below this video. You may want to donate. Alright, you may want to donate to them. Alright, donate something from to them in order to make their simulations, or in order to create more simulations in the future. Alright, so let's go right into it. Okay, so we have right here a simulation that will showcase the differences between real and ideal gas. Okay, now in an ideal gas, okay, since the molecules are sparse, okay, since the molecules are sparse, we treat these molecules as dimensionless points since they are sparse. Okay, what do you mean by sparse? They are scattered, okay, and they are few. Okay, as you can see here, we have a few molecules that we have over here. Okay, so we just have 19 molecules that you have over here. Okay, so since there are few, then therefore we can treat the volume as dimensionless. Okay, so there's no volume here, so the volume there is negligible, zero. All right, so zero, the volume is zero. All right, next one. How about what will happen? What will happen if we apply a high pressure? All right, so what will happen if we increase the pressure? Okay, so by compressing the volume, we have a high pressure over here. Okay, we have a high pressure. So what does it tell us? Now we can now say, all right, so we can now say that the gas molecules here have now a volume. Okay, because it is the gas molecules is subjected to high pressure. Okay, so the molecules are subjected to high pressure. So we can safely say that the volume here is somehow very, very small, but it is non-zero. That is the most important thing. Although it is very small, but it is non-zero. Okay, so we can now have a volume here at high pressure. Okay, so first deviation that we have right here from ideal gas is that we can have a volume, we can have a small value of volume if we have high pressure. Okay, so we can have a small volume if we have a high pressure. The next one. Okay, how can we achieve an interaction? All right, so how can we achieve an interaction that we have over here? How can we achieve that one? We can achieve that interaction or interactive forces by decreasing the temperature. As you can see, as you increase the temperature right here, okay, since the gas molecules are moving faster, okay, since the gas molecules are moving faster, interactive forces are negligible because they are moving faster. Okay, they are going somewhere else and they are moving faster. Okay, so that what happens to the interactive forces? It is negligible. But if we decrease the temperature, all right, if we decrease the temperature to near absolute zero, as you can see, the movement of the molecules is somehow very slow. All right, so the movement of the molecules is very slow. Now, what is the connection on that? All right, what's the connection on that on the interactive forces? Now, take a look at this molecule. Alright, so take a look at this. Now, when they are moving very slow, when these molecules are moving very slow, they tend to stick for a longer period of time with another gas molecule. Alright? So, they can stick with they can interact with another gas molecule for a longer period of time because they are moving slowly. Okay? So, it means that there is an attractive, possibly, there is an attractive or repulsive force. Okay, there is an attractive and repulsive force that can happen if the molecules of these gas particles moves slowly. You get the point? Alright, so the next deviation, the second deviation from ideal gas is low temperature. Okay, the first one is high pressure. The second one is low temperature. Right, so those are the deviation from ideal gas law that we have right here. Alright, so you have seen the simulation. Then we can safely conclude that ideally, volume of the gas molecules are negligible. But that is negligible if the pressure is very low. But if you increase the pressure, the volume now is significant. Okay, so the volume of your gas molecules are now being significant. Okay, so that's the difference between real gas and ideal gas. Okay, so at high pressure, volume is significant. All right, so next one. Now, that's the reason why, since the real gases have volume, so we can apply volume correction. Okay, most of the time, the real gases volume is less than the ideal gas. Okay? the real gas volume is somehow less than to the ideal gas that we have. All right. So the actual volume, all right, free to move in is less because of particle size. So what do we mean by this one? Okay. Now, if the particle size of the gas molecules is large, all right, you can see the volume, or the volume is somehow significant. Okay, but if the particle size of the gas molecules is very small, volume is somehow negligible. Okay, is somehow negligible. So particle size plays an important factor here. All right, next one. This is logically true. Okay, that more molecules will have more effect on the volume. Okay, so let's do that one in the simulation. Okay, let's reset the simulation and let's pump a lot of molecules that we have right here. Okay, now as you can see here, in a if you have less molecules of gas inside a certain container, then volume is somehow negligible. Okay, but if you have a lot of molecules or a lot of gas inside that particular container, okay, if you have a lot of gas inside, then the volume of your gas is somehow significant, especially when you apply high pressure on it. Okay, especially when you apply high pressure on it, the volume is definitely significant in this case. Okay, so more is better. Okay, more is better in terms of volume that we have right there. Okay. Okay, so that is why the corrected volume that we have right here is V minus N times B. All right. So what is this B? B is a constant. So I will show you later the table. B is constant, and B differs from each gas. Okay, for each of every gas. Okay, not all gases are created equal. Now, the B talks about the particle size, something like that. B talks about the particle size, and the greater the particle size, all right, of the particular gas molecules, the greater effect will be on its volume. Okay, something like that. Okay, so that's the B. So I will show you that one later when we go to the pressure correction. Okay, since we encountered earlier the pressure correction that we have over there, the high pressure, the higher the pressure, the more the gases will collide, okay, on your container, and the more noticeable the volume will be. Okay, so okay, the pressure depends on the number of molecules per liter. So meaning to say that the number or the more molecules of gas, like the one on the simulation that we have earlier, the more molecules of gas, the more pressure, all right, the more pressure differences you will notice. Okay, and one thing is very important here. Two molecules should interact with each other. Okay, so two molecules should interact. So that is the reason why in this formula that you have right here, it is the formula on the formula itself, there is a square. Okay, on the formula. Okay, so there's a square over here on the formula that talks about these two molecules of gases that interacts on your system. Okay, so hey, I forgot this one. The molecules are attracted to each other. The pressure on the container will be less, somehow less ideal. Okay, so again, if the molecules of your gas are somehow polar or non-polar, it has a certain effect on the pressure differences. Okay, it has a certain effect on the pressure differences. So polar molecules have greater effect than non-polar molecules. Okay, so that's the thing about this pressure that we have over here. So let's take a look at the simulation one more time. Okay, so as you can see here, the more molecules that you have over here, the greater the pressure. Okay, so the greater the pressure difference that you have. Now, the higher the pressure, the more noticeable the volume. Okay, so if we going to reset this one, okay, so if we're going to decrease the particles that you have over here, right, so as you can see, inserting 50 particles of gas that you have over here, okay, so the pressure is less. So somehow there's a volume still, there's a value on the volume still, but the thing there is it's not that great. When you increase the number of molecules, that's the volume starts to become significant, okay, at the end of the day. Okay, so that's the thing here, okay, about the pressure. Okay, now integrating this volume correction and pressure correction in your ideal gas will give you this van der Waals equation that we have right here. Okay, it will give you the van der Waals equation that we have right here. So it states that we have the P is the pressure correction on P is added with the A, the constant A that we have, and we have the number of moles over here and the volume multiplied to volume and the volume correction that you have over here, and the nRT is still the same, nothing changed on the nRT side. Okay, now what determines the answer here? Okay, what determines the answer? The bigger molecules, okay, have larger B. Okay, and A depends on the size and then the polarity of the molecules. Now, this equation was formulated by none other than Johannes Diederik van der Waals. Okay, he is a mathematician and physicist from Netherlands. Okay, now because of this equation, experiments using gas laws or experiments using certain gases can be accurately determined. Okay, so the answer on this van der Waals equation will give you an accurate answer. All right, will give you an accurate results on whatever gas that you are studying, as long as you apply the pressure correction and the volume correction for each of every gas that you will use. All right, so what is this A and B constants that we have? Okay, so these are the A and B constants. Okay, so for ammonia, we have 4.170 and the B constant is 0.03707. Okay, so what does it mean? Okay, what does this one mean? It means that sulfur dioxide has a larger size compared to ammonia in terms of particle size. Okay, so sulfur dioxide is big. Okay, it's bigger than ammonia. Okay, and more so, sulfur dioxide is bigger than hydrogen. Okay, so hydrogen gas. Now let's take a look at the A. Okay, so the A talks about the polarity. Okay, it talks about the polarity. The larger the A, like the one that you have right here, this is polar. Okay, so polar. This one also is polar, but the smaller, the more as the A decreases, okay, like the one that you have right here, this one over here, this three over there, as the A decreases, the molecules is starting now to become non-polar. Okay, so the molecules starts to become non-polar. Okay, so the most non-polar gas molecules that we have right here is the hydrogen. That is a very non-polar molecule that you have over here. Okay, so that's their differences. Okay, again, the larger the value, the more polar it is. The smaller the value, the more non-polar the molecule it is. Okay, so they are all constant, so don't worry. Okay, don't worry on having or finding out what is the value of A and B. They are all constant. So we call this constant as van der Waals constant for several gases. All right, so that so you know already what is the van der Waals constant. Okay, so let's try to find out. Okay, let's solve some sample problems and compare these problems that we have right here. Let's compare these sample problems that we have right here using the ideal gas law and the van der Waals equation. Okay, so let's for this first sample problem that we have right here, let's solve for the pressure. Okay, let's solve for the pressure. Now, I have right here a volume of 6.78 liters. Okay, and I have right here the number of moles as 2.05 mole of oxygen. Okay, so if we take a look at oxygen at this table, oxygen is somehow it is a nonpolar molecule. Okay, and it has a very small particle size. Okay, oxygen has a very small particle size. Alright, so temperature is 340 degrees Celsius plus 273, that will be around 600 plus, alright, Kelvin. Alright, so with that, what are we going to use here? So we will going to use the ideal gas law and compare it with the van der Waals equation. Okay, to the results of the van der Waals equation. All right, so let's take a look on that. All right, so upon calculating the ideal gas law and comparing it with the van der Waals equation that we have right here, so let's take a quick look on what are the things that happened here. Okay, so in the ideal gas law, we derived the equation that we have right here in order to compute for the pressure, and here we are now plugging all the variables that we have right here, canceling all the similar units. Okay, so don't forget the R value. Okay, the R value should be somehow similar to each and every unit that you have right here. Okay, so canceling all the units that you have, okay, similar units that you have right here, we got 15.22 or 15.2 atmosphere. Okay, so we got 15.2 atmosphere using the ideal gas law. Now, upon using the van der Waals equation, the one that you have over here, okay, so rearranging the formula, it gives us this particular equation. Okay, so using this equation that you have over here, we will be able to compute what is the pressure using the van der Waals equation. Now, upon doing so, we plug all the necessary variables that you have right there. Now, especially this one, the A and B. Alright, so the A and B. Okay, so this is the A and this is the B over here. Alright, now where did we get this value? Now, this A value and B value, we got this from this table. Now, the A value is the oxygen that you have right here, and the B value is for the oxygen that you have over here. So, this is the B value. So, if I remove this one, so this will be the B value and this will be the A value that you need in order to solve that particular problem. Okay, so let's go back to it. Okay, so let's go back. Okay, so there you go. Now, applying all the necessary cancellation, okay, so applying all the necessary cancellations that we have right here, so we cancel the liters, okay, we cancel the moles, we cancel also the Kelvin, alright? So, on the other side also, we cancel everything except for the atmosphere. Okay? So, atmosphere over here. Because that is what we wanted. Okay? That's the unit that we wanted. Alright, so, upon doing the correct mathematical computation that we have right here, upon doing the correct mathematical operation, we got 15.2 atmosphere. Okay, so we got the 15.2 atmosphere. Now, the question here is, why is it the same? Okay, so why is it the same? One reason is because the temperature is very high. Okay, the temperature that you have over here is very high, 613.15. Okay, so we have a high temperature over here. So that's the reason why there is no significant difference between the two formulas that you have right here in terms of their results. But if you will apply a low temperature, okay, if you will apply a low temperature, does it have Okay, can we see a deviation between the ideal gas formula and the van der Waals equation? Can we see a deviation on that? Okay, so let's take a look. Right, so upon changing this one, so we will going to change this. Okay, so negative 10 plus 273. Alright, so negative 10 plus 273.15 Kelvin. So that will give us 263.15 Kelvin. So this is what we will going to plug on that particular equation. So we will not change everything here since the volume, alright, so the volume, the number of moles are still the same. We will only change the temperature and see if there is a deviation that we will notice between these two formulas that we have right here. So we have 263.15 Kelvin. Again, apply all the cancellation. Now, doing so, the pressure that we will get is 6.53 atmosphere. The pressure that we will get is 6.53 atmosphere. Alright? So that is for the ideal gas law. Ideal gas. Now, meanwhile, alright, so in the van der Waals equation, all we need to do here is, since the temperature is only the one change here, so we will erase this one and change it into 263.15 Kelvin. Okay, the volume and the number of moles is still the same. We have the same number of A and B. Okay, so let's check. Okay, final checking. Okay, so everything is good and ready to go. Okay, so we can compute now. Okay, so upon computing earlier, so we get the pressure as 6.47 atmosphere. Alright, so 6.67 atmosphere. This is for the real gas. Okay, using the van der Waals equation. Now, if you will going to ask which one is accurate, is it for the ideal gas or the real gas? So, we can safely say that the one that is more accurate is the real gas, not the ideal gas. The ideal gas is only for assumptions. Okay? So, the number that we have computed here is not that bad after all. Alright, so since we got the value or we got the results from the van der Waals and the ideal gas law and agreed that the real gas is more accurate than the ideal gas, okay, so the van der Waals equation is more accurate than the ideal gas, okay, so as you can see here, the value, alright, so the value of pressure is somehow very small in terms of difference, okay, but if you want to challenge yourself, instead of using oxygen, you may use other gas molecules like ammonia, neon, water vapor, sulfur dioxide, and compare the results, okay. And not only that, you can use a very low temperature. You can still use the same value that you have right here, and instead of having negative 10, try using negative 50 degrees Celsius and try to find out what will happen to the value of the result that we have right here. Compare it with this result. What will happen if you have a negative 50 degrees Celsius temperature? Alright? So, do you think a negative 50 degrees temperature will have a certain deviation? Alright? So, it will have a certain deviation over the results of your van der Waals equation that you have right here. Okay, so let me know in the comment section if you did that particular challenge. So let me know what is the value of pressure at negative 50 degrees Celsius. Okay, so that is the van der Waals equation and the ideal gas formula. Alright, so disclaimer, you can only use the van der Waals equation if you are using gas molecules during your experiment. Okay? So if you are performing or if you are conducting an experiment or investigation, van der Waals equation is very accurate. Alright? It's very accurate in terms of presentation of the results of these gas molecules. Okay? But in simple computations, that like the one that we will have later, Okay, ideal gas law formula is very handy, okay, for those computations. Okay, so with that, okay, so what are the possible applications of ideal gas law? Alright, so what are the possible application? So we have here the breathing, okay, one of the application. Next one is the compressed, okay, like the one that you have right here. These are the compressed gas can. Okay, and we have right here the pressurized gas tank that we have over here, the oxygen tank, which is used in hospitals. Okay, it uses the idea of the ideal gas law. Okay, next one, the gases inside this soft drinks can. All right, so soft drinks in can, the gases inside. And finally, we have the cabin of the airplane. Okay, not only the cabin of the airplane but also the cabin of a submarine. Okay, so the pressure difference, okay, so the pressure differences must be maintained from outside and inside. Okay, so the pressure inside the cabin of the airplane must be maintained at 1 atmosphere. Okay, so that's the normal or the standard pressure in which humans can tolerate. And the one that is outside this airplane has much lower. It contains lower pressure compared to the one that is found inside the cabin. Okay, so the reason why, it's because the higher the altitude, the lower the pressure. Okay, so that's the pressure here. Now, if the pressure inside the cabin suddenly drops, what will happen? It will deploy some oxygen mask inside the airplane. It will deploy some oxygen mask, and it will help the people inside to breathe easier. Okay, so those oxygen masks are deployed in terms of emergency landing, something like that. Okay, unexpected turbulence, something like that. So the pressure difference inside the cabin can significantly decrease, okay, in those cases. Okay, so these are the application of ideal gas law in real life. Okay, so let's check first if you learned something from this first part of our lesson that we have right here. Okay, so the first thing that we have right here is all about the real gas. Under what condition does the gas, or does a gas deviate from ideal gas behavior? Okay, so you can pause the video and think of the answer. Okay, or you can go back. Okay, you can go back to this video. You can play it backwards. All right, and try to find out what conditions does a gas deviate from ideal gas equation or the gas behavior. Okay, so the answer here is high pressure and low temperature. Under these two conditions that we have right here, gas deviates. Alright, so gas deviates from ideal gas behavior. Okay, high pressure and low temperature. Alright, the second question, what two parameters of non-ideal gas contradicts the postulate of the kinetic molecular theory? Alright, so what are these two parameters? So you can pause this video if you want to think of the answer and try to find out on this video what is the possible. All right, what is the possible answer to this question? What are the two parameters? Number one, all right. So number one, what are the two parameters of the non-ideal gas? That gases have small volumes. Alright? Gases have small volumes at high pressure. Alright? And the second one is gases have, or gases interacts. Okay? Gases have an interaction. Interaction with other gas molecules at low temperature. Alright, so these are the two parameters. Gases have small volumes at high pressure. And the second one is gases have an interaction with each other. These are attraction and repulsive forces, okay, with the other gas molecules at a very small amount. Okay, at what condition? At low temperature. Alright, so these are the two parameters in which the non-ideal gas contradicts the postulates of the kinetic molecular theory. Alright, so the next one that we have right here is the sample problems using the ideal gas law that we have learned on this video lesson. Alright, so here we are in the first sample problem that we have right here about the ideal gas law. Okay, so in these sample problems that we have over here, we will try to find out how to use the ideal gas law in solving word problems, okay, related to that. Okay, so the first one that we have here is the... Okay, so let me read the problem. So dinitrogen monoxide, or N2O, which is also known as the laughing gas, is used by dentists as an anesthetic, okay, for anesthetic purposes. If 2.86 mole of gas occupies a 2.0 liter tank at 23 degrees Celsius, what is the pressure? Alright, so what is the pressure in the tank, okay, in the dentist office? Okay, so that's the question. Alright, so first things first, we need to what we need to do here is to write down all the given variables. Okay, so first thing that we saw on the problem is that we have 2.86 moles. Okay, so we are very lucky that it is already converted into moles. Okay, so we have 2.86 mole, okay, of N2O. Okay, the next one is this one, which is the volume. Okay, so that will be 2.0 liters. And we have the temperature over here, 23 degrees Celsius. Alright, so the temperature is 23 degrees Celsius plus 273.15. So that will be 296.15 Kelvin. Alright, so that will be the variables that we have right here. And we are asked to compute for the pressure. Okay, so in this case, we can use the R. Okay, so we can use the R here as 0.0821 liters atmosphere over mole Kelvin. Okay, so that is the R that we will going to use here, and we will convert it later. The final answer will be converted later to millimeters of mercury. Okay, so let's take a look at the equation that we will going to use. Certainly, we will going to use the ideal gas law here. Okay, and since we are asked to compute for the pressure, so it is very simple. So pressure is equal to nRT over V. Okay, so there you go. Then let's plug all the necessary values on our equation. So we have 2.86 moles times 0.0821, okay, liters atmosphere mole Kelvin. Alright, and temperature, which is 296 so 296.15 Kelvin. Alright, over we have the volume, which is 20 liters. Okay, so we cancel all the similar units that we see on this computation, and we compute now. Okay, so what will be the pressure? So 2.86 times 0.0821 times 296.15 divided by 20. So that will be 3.47. Alright, so we will use 4 decimal place because this is not yet the final answer. So the pressure will be 3.4769. Alright, so 3.4769, that will be in atmosphere. So the problem is asking us to convert it into millimeters of mercury. So that is very simple. So if you know the conversion factor, so we have atmosphere, 1 atmosphere is equal to 760 millimeters of mercury. Okay, so cancel the atmosphere. Then the pressure is 3.4769 times 760. So the answer is 2,642. Alright, 2,642 2,642 millimeters of mercury. Alright, so that will be the final answer. So millimeters of mercury, I forgot to include the statement. Okay, so 2,642 millimeters of mercury is the pressure on the tank. Okay. Right, so 2,642 is the pressure on the tank on the dentist, in the dentist office. Okay, so that is our first sample problem for the ideal gas law. Alright, so we have now the second sample problem for the ideal gas law. Okay, so in this sample problem, we are dealing with two sets of problem that we have right here. The first one is to calculate the volume of 4.5 rather moles of sulfur dioxide measured at STP. And on letter B, what volume would this occupy at 25 degrees Celsius and 150 kilopascal? Solve this in 2 ways. Alright, so there are 2 ways to solve this one. Okay, so on letter A, alright, on letter A, this is very simple. You don't need the ideal gas law to solve letter A because that is already in STP. Okay? Now, all you need to have here is the idea using the molar volumes in Avogadro's law. Okay? Using the molar volumes in Avogadro's law, you will be able to solve letter A. Now, if you don't know what is Avogadro's law, the link will appear above. So, you need to watch that one first for you to have an idea what is this Avogadro's law and how can you use that law in this particular problem. Alright, so let's solve this one. So we have for this one, we have 4.50 mole. That will be our N over here. Okay, of SO2. Alright, SO2. Hey, and next one that we have here in the problem, we have the temperature, which is in 25 degrees Celsius or more or less 273.15 plus 25. So that will be 298.50. Right, so 298.15 Kelvin. And we have the pressure. Alright, so we have the pressure. In terms of pressure, you can use the kilopascal. Alright, so you can use the kilopascal, but you should be careful on your R. Okay, if you use kilopascal, then your R should be in kilopascal as well. But in this case, I will going to use atmosphere because it is much simpler than kilopascal. Okay, so 150 kilopascal. So that is around in atmosphere. So that will be around 150 over 101.325. Okay, so that will be 1.4803 atmosphere. Okay, so our R is not anymore in kilopascal. We will going to use liters atmosphere over mole Kelvin. Alright, so now let's answer first letter A. Okay, so how do we deal with letter A? Okay, so using the Avogadro's law, we will be able to deal with letter A in a more easier path. Okay, so we have 4.50 mole, alright, SO2, and using the molar volume, so 1 mole is equal to 22.41. Alright, 22.41 liters. So we will now be able to compute for the volume. Alright, so we have 1 mole to cancel the mole on this side and 22.41 liters. Okay, so cancel the mole and what do we get? Okay, so the volume at STP, alright, so the volume at STP, so 4.50 times 22.41. Then the answer will be 100.8 liters. Alright, so 100.8 liters is the volume of SO2 at STP. There you go. Okay, so that is the new volume. Alright, next one. The next problem is not anymore in STP. Okay, if the problem is not anymore in STP, so what are we going to do? Okay, what are we going to do on that? We will use the ideal gas law. Okay, so upon using the ideal gas law over here, so PV equals nRT. Okay, so let's try to find out. Since volume is the one that is missing, this is very simple. Alright, so volume is equal to nRT over T. Okay, so this is our formula over here. And we can now compute for the volume. Alright, so okay, let's plug in those informations. So we have 4.50 moles times 0.0821, alright, liters atmosphere and mole Kelvin. And the others, for the temperature, we have 298.15 Kelvin. Alright, so we have now this first part. And on the bottom, we have 1.4803 atmosphere. Alright, so let's cancel all the similar units. So cancel, cancel, cancel. Okay, so what do we get? Okay, so 4.50 times 8.021 times 298.15. Okay, so that will be 110 divided by 1.4083. So that will be, okay, so the volume is 74. Okay, so the volume is 74.4 liters. Okay? Okay, so the new volume is 74.4 liters is the volume of SO2 at 25 degrees Celsius and 150 kilos. Alright, so that is the final and complete answer. Okay, if I can do it, you can do it as well. Alright, so let me know in the comment section if you got the same answer as mine. Alright, so that's the thing here. Okay, so this is the second sample problem. Alright, so we have now the third problem that we have over here. Okay, so what is this third problem? The third problem is very different because we can use the ideal gas to find out or to predict what kind of gas are we dealing with. Alright, so let me read the problem. So 98 milliliters of an unknown gas weighs about 0.0870 grams. Okay, at STP. Calculate the molar mass of the gas. Can you determine the identity of the unknown gas? So that is the trickiest, or that is the challenging part here. Okay, can we identify the unknown gas? Is it possible? Yes, it is, with the use of the ideal gas law. Okay, so you can pause this video You can pause this video and try to predict for yourself, and for you to see if your answer is correct, you can play this video after you try answering it. Okay, so let's solve for this problem. Okay, so we have 98 ml. So 98 ml, probably this is the volume. Okay, so no doubt about it. Okay, and we have the mass. Okay, and what do we have right here? Okay, so aside from the volume and then the mass, okay, we have at STP. Alright, so we have it at STP. Okay, so okay, only the volume is not at STP. Okay, so we can somehow okay, we can somehow say that the pressure is at STP and the temperature is at STP. Okay, so let's write them all down. So the mass, that is 0.0870 gram. Okay, and we have the volume, which is the 98 ml. Okay, which is that is equivalent to 98 over 1000. So that will be 0.098 liters. Alright, so that is in liters. Okay, because the R that we will going to use is in liters. Okay, so next one, how about the pressure? Since that is in STP, so the pressure is 1 atmosphere. Very simple. And temperature, 0 degrees Celsius. Alright, so 0 degrees Celsius or 273.15 Kelvin. Okay, so what do we have right here? Okay, what do we have? We are missing. Now, if we were going to take a look at this, so we have the R, which is 0.0821 liters atmosphere mole Kelvin. Alright, so if you're going to take a look at this, the only missing thing that we have here is the N. Right? So the N, that is the missing here. Okay, so since we are certain that N is missing, so we can use this formula, PV is equal to nRT. Okay, so PV is equal to nRT. Then since the N is missing, so N is equal to PV over RT. Okay, so let's this is our formula and we are good and ready to go. Okay, so let's plug in all those values. So we have 1 atmosphere and the volume is 0.98 liters over the R, which is 0.0821 liters atmosphere over mole Kelvin, times the temperature, which is 273.15. Okay, so we have to cancel this one, sorry, so the mole is what we are looking for. Okay, so be careful on what you canceled. Okay, be careful on what you cancel on this computation. Alright, so we have atmosphere canceled and liters is also canceled. Alright, so let's solve for the okay, so 0.0821, so since this is multiplied by 1, so there's no problem on that, times 273.15. Okay, so we have 0.098 over 22.42256. Okay. Okay, so the answer will be 4.37 times 10 to the negative 3. Alright? 4.37 times 10 to the negative 3 moles. Alright, of that unknown gas. Okay, so since we got the N already, is it possible to solve for the unknown gas? Is it possible to solve for the unknown gas? Yes, it is possible because we have this one already. Okay, now how do we solve for the unknown gas? Okay, all we need to do is to get the unknown gas. Okay, so we have the mass over N. Okay, that's how you get the molar mass. Okay. Okay, so the mass or the molar mass is obtained by dividing mass over the N. Okay, so let's plug in those values. So the mass is 0.0870 grams over 4.37 times 10 to negative 3 moles. Okay, remember, molar mass has a unit of grams per mole. Okay, so grams per mole. Okay, so let's compute. So what will be the molar mass? Okay, so what will be the molar mass? And possibly what is the element? Okay, so 0.0870. Okay. Okay, so 0.0870 over 0.00437. Okay, so the answer is 19.9. Alright, so 19.9 grams per mole. Okay, so this is grams per mole, not 9. So grams per mole. Okay, so that is not the answer. Can you determine the identity of the unknown gas? Now, let's take a look. Alright, so let's take a look at the periodic table if there is such 19.9 grams that we have over there. Okay, so periodic table. So what is this gas? Okay, so what is this gas? So 19. Okay, 19. Alright, so 19. 19.9. Okay, so this is, if you round, alright, so if you round 19.9, it is somehow equivalent to 20. Okay, if you round 19.9. So we can predict, alright, so we can predict that the 19.9 or the unknown gas is neon. Okay, so this is neon. Okay, so it will not be any other element because chlorine has 35. That is impossible. Fluorine is 18, which is or 19, which is somehow impossible because 19.9 is our result. Okay, the only gas, alright, so the only gas that is near 19.19 or 19.9 is neon. Okay, so let's go back to our solving board. Okay, so the unknown gas, alright, so to complete the statement, so the unknown gas is neon. Okay. Alright, so that is the, okay, so that is for the third sample problem for the ideal gas law that we have right here. Okay. Alright, so we have now the fourth problem for this ideal gas law lesson that we have right here. Okay, so the ideal gas law is also handy in solving gas stoichiometry problem. Okay, so if you remember in the Avogadro's law, there is a part there called the gas stoichiometry in which you will use the Avogadro's law to solve problems related to chemical reactions of gases. Okay, so in this case, okay, with the use of the ideal gas law, we will be able to compute the gas stoichiometry problems that are not in STP. Okay, remember Avogadro's law always Avogadro's law or the molar volume in the Avogadro's law is used when the conditions is at STP. But what if the condition is not at STP? What are we going to do? We will going to use the ideal gas. So no problem on that. Okay, so let's have this one first. So how many liters of oxygen are needed to react? Okay, so how many liters of oxygen are needed to react to 28 grams ammonia at 24 degrees Celsius and 0.950 atmosphere? Okay, so this is the equation that we have right here. Now, the first thing that you need to do if you are dealing with the gas stoichiometry problem is make sure, okay, is that you make sure that this equation is balanced. Okay? Now, if the equation is not balanced, you will have a problem. Okay? So you will have a problem at the end of the day. So that's the thing here. Okay, so let's balance this equation first before anything else. Okay, so we have ammonia plus oxygen, we have nitrogen oxide, and so water. So we can have it 4 over here. I will erase this one. Okay, so we can have 4 here. And possibly we have 5 over here. Okay, so if that is 10, okay, if the oxygen here is 10, so therefore we can have it 6. Okay, we can have it here 6 and 4 over here. 6 plus 4, 10 oxygen. 6 times 2, 12. So let's see, 4 times 3, 12. Okay, so that is perfectly balanced. And the nitrogen, 4, perfectly balanced, as all things should be. Okay, so now, if the chemical equation is balanced and these are correct, then we are good and ready to go. Okay, so let's solve this one. Okay, so let's write all the things that we have right here. So we have how many liters? Okay, so we are computing for the volume because that one is missing. Okay, and we have 28 grams. All right, so we have the mass. Okay, now the mass will be converted to moles. Okay, will be converted to moles. That is a mandatory. All right, before you compute for the ideal gas, you should need to convert it first. Okay, so we have 28.0 grams. Alright, so we have 28.0 grams NH3. Okay, so times. Okay, so what do we have right here? In order to convert it into moles, what we need here is the chemical equation, right? And also the targeted gas that we are going to work on. Okay, so we need to convert NH3 to moles first. So we have the mole. Okay, so we must get the molar mass of NH3. So what is the molar mass of NH3? So we have 14. Okay, so 14.01. Okay, times 1.01 times 3. Okay, rather plus. Okay, plus 1.01 times 3. Okay, so we have here 17 point okay, so let me check. All right, so 17.04 grams. Okay, so 17.04 grams is the molar mass of the ammonia that we have right there, and multiplied to. Okay, so multiplied to, since moles are what we need, okay, moles of oxygen, liters of oxygen is what we need here. So this is NH3, so mole of NH3. Then using the chemical equation that you have right here, we can plug here the number of moles of NH3 on the equation. So we have 4 NH3. Okay, so we have here 4 NH3 over here, and our target oxygen. Okay, so we have 5 oxygen, 5 moles of oxygen. Okay, then that's it. Okay, we don't need to convert it into grams anymore. We don't need to convert it into grams because it's already in moles. Okay, so what will be the answer? Okay, so the answer here will be, okay, so cancel the grams. So 28 over 17.04 times 5 divided by 4. Okay, so the answer is 2.05 mole, or 2.053, all right, or 4 rather, mole O2. Okay, so we are done with the N. Okay, so this will now be our N. Okay, next one. How about the temperature? Okay, so the temperature is 24 degrees Celsius. So that is 24 plus 273.15. So that will be 297.15. 297.15 Kelvin. Okay, so the next one is what do we have on the problem? So we have the pressure. So we have 0.950 atmosphere. Okay, so we are looking for the volume and okay, so let's try to find it out. Okay, using this equation, so PV is equal to nRT. And since we are looking for the volume, okay, so since we are looking for the volume, so volume is equal to nRT over P. Okay, so this is our formula and let's plug in everything. So we have 2.05 mole. Okay, 2.054. Okay, so I forgot that. Okay, mole multiplied to, okay, so I forgot the R. Okay, so the R is 0.0821 liters atmosphere mole. Yeah. Okay. All right, so let's put it right here. So 0.0821 liters atmosphere mole Kelvin. Okay, and multiplied to the temperature, which is 297.15 Kelvin. Okay, divided by the pressure, which is 0.950 atm. Okay, so cancel all the similar units. Cancel. Kelvin, cancel. Mole, cancel. Then we have the liters. Okay, so that's what we are looking for. So what will be the volume? Okay, let's compute. Divided by 0.950. Okay, so the answer will be 52.7 liters. Okay? Okay, 52.7 liters is the amount of oxygen needed to react on 28 grams of ammonia. Alright, so that is the final and complete answer. So, okay. So, I will remove myself there. Alright, so for you to see the answer. Okay, so that is 52.7 liters is the amount of oxygen needed to react on 28 grams of ammonia. Alright, so that was the third or the fourth sample problem using the gas stoichiometry. Remember, always balance the equation first before you do the calculations. Okay, so let's go now to the next sample problem. Okay. Alright, so we are now down to the fifth and final sample problem for the ideal gas law lesson that we have right here. And fortunately enough, our final problem right here is a gas stoichiometry problem, which enables us to integrate the ideal gas law. Okay, so let me read the problem for you. Okay, so aqueous lithium hydroxide solution is used to purify air in spacecrafts and submarines because it absorbs carbon dioxide, which is an end byproduct of metabolism. Okay, so according to the equation, lithium hydroxide reacts with carbon dioxide, produces lithium carbonate and water, okay, at the end of the chemical reaction. Okay, now the pressure of carbon dioxide inside the cabin of a submarine having a volume of 2.43 times 10 to the 5th liters is 7.93 times 10 to the negative 3 atmosphere at 312 Kelvin. A solution of lithium hydroxide of negligible volume is introduced into the cabin, and eventually the cabin pressure falls to 1.23 times 10 to the negative 4 atmosphere. How many grams of lithium carbonate are formed in this process. Alright, so now you can pause this video, alright, so if you want to answer it on your for yourself, and play the video after you have found the answer. Okay, so let's try this one out. Okay, now what do we have right here? Okay, so first things first, check the equation if it is balanced. Okay, so let's check the equation if it is balanced. 2 lithium. Alright, 2 lithium, so check. So 2 oxygen plus 2, 4. Alright, so 3. Alright, so we have over 3 here. Then plus 1, 4. Okay, so check. Oxygen is check. Next one is hydrogen. Alright, so the hydrogen, we have 2 over here and 2 on the other side. Okay, check. They are balanced. And we have the carbon dioxide. We have 1 carbon here, or 1 carbon here, and we have 1 carbon over there on the product side. Okay, so definitely this equation is balanced. Sorry. Alright, so this equation is balanced, and we are now good in for the calculations. Okay, so let's write everything that we have right here. First one, we have, okay, so first one is the volume. Okay, so how many grams of lithium carbonate is formed in this process? Okay, so the volume. Okay, so we have here the volume of carbon dioxide. Okay, so that's the first one. Next one, we have the temperature. Okay, and we have these 2 pressure that you have right here. This is the initial pressure. Okay, and this is the change in pressure that you have. Okay, now we will compute for the final pressure after this drop. Okay, we will compute for the final pressure after this drop. And the problem is asking us how many grams of lithium carbonate are formed in this process. Okay, so with that, let's go and solve this problem. Alright, so we have written all the data that we have on the problem that we have right here. Okay, so we have written all this variable that we got from the problem, and the problem is asking us for the mass. Okay, so the mass of the lithium carbonate. Okay, mass of lithium carbonate that will be produced, okay, in this process. So liters of carbon dioxide. Okay, so that is the liters of carbon dioxide. Okay, now how we will do this one? Okay, so since we have 2 pressure here, now don't panic with regards to these 2 pressure that we have right here. Now if you read the problem according, or if you read the problem properly, okay, if you read the problem properly, the other one says that the pressure falls. Okay, the pressure falls to 1.23 times 10 to the negative 4 atmosphere. So meaning to say that we will subtract 1.23 to 7.93 that you have over here. Okay, now doing so, alright, so doing so, if you subtract these two together, okay, so 7.93 times 10 to the negative 3 minus 1.23 times 10 to the negative 4, you will get 7.8, alright, 7.881 times 10 to negative 3 atmosphere. So this is what we will going to use, this one, okay, for the pressure. Alright, so we have here the volume. There's nothing wrong with the volume. The temperature is already in Kelvin. And upon using the ideal gas, so to compute for the mass that we have right here, we need to find out first what is the N. Okay, using the values that you have over here. Okay, so let's find out what is the N of your carbon dioxide. Okay, so using this formula, PV is equal to nRT. And we are asked to find out the N. So the N is equal to PV over RT. So that is the formula that we will going to use on this problem. And let's compute. Okay, so let's plug in all those values that we have over here. So the pressure is 7.81. Alright, 7.81 times 10 to negative 3 atmosphere. Okay, multiplied to the volume of 2.43, okay, times 10 to negative 5. Alright, so that will be in liters. Okay, over we have okay, so I forgot the R. So the R that we will going to use is, since this is in atmosphere, so we don't have any problem on that, 0.0821 liters atmosphere mole Kelvin. Alright, so we have 0.821 liters atmosphere mole Kelvin. Right, so okay, so that will be our R, and the temperature that we will have right here is 312 Kelvin. Okay, so we need to cancel out everything except for the mole. Okay, cancel. Okay, so we have the mole as remaining unit that we have. Okay, so let's compute. Okay, so let's do this one at a time. So this is not negative 5. Okay. Okay, so you might be confused. Okay, so we have 7.81. Okay, times 2. All right. Okay, so that will be 1. All right, that will be 18.9783 times 10. Okay, times 10 raised to. Okay, so 2. Okay, so as you can see, I did not arrange the scientific notation properly because I am not yet done with the computation. So it will be automatically arranged properly. Okay, so that will be 18.9783 times 10 to the 2. Okay, so unitless. Okay, so on the one at the bottom, so we have 0.0821 times 312. Alright, so that will be 25.6152. Oh, that will be in mole. Okay, so let's compute for the N. So what will be our N? Okay, so the N will be 18.9783 over 25.6152. Okay, so the answer is alright, so the answer is 0.74. Okay, so 0.7409 times 10 to the 2. Okay, so if you were going to arrange that one, 0.7409 times 10 to, or okay, so that will be 74.9. Okay, so that is 74.09 okay, mole. Okay, so that will be 74.09 mole. Okay, that is carbon dioxide. Okay, so that is for your carbon dioxide. Now, the problem is asking what is the mass of the lithium carbonate. So, all we need to do here is to do the gas stoichiometry. Alright, so we need to convert this one into, okay, we need to convert this one into lithium carbonate. So we have 74.09 moles carbon dioxide. Then let's take a look at the, okay, so that will be 1 carbon dioxide, so this one, and we have 1 lithium carbonate, our target. Okay, 1 lithium carbonate. Sorry. Erase. So 1 lithium 2 carbonate. Okay. Times. Okay. So I will remove myself here. Dang. Alright. So times, let's go for the mass of the lithium carbonate. Alright. So 1 mole of lithium carbonate is equivalent to. Alright. So let's take a look at the periodic table. Alright. So the periodic table, lithium is 6.94 times 2 plus carbon 12.01 times okay, so plus oxygen 15.99 times 3. So that will be 73. Alright, so that will be 73.887. Alright, so 73.887 grams. Okay, so let's cancel the mole. Cancel. Okay, so we are now done with the whole process that we have right here. Okay, so we are now done with the whole process, and what will be the mass, okay, that we are looking for? So 74.09 times, okay, so since that is 1, so 73.887. Okay, so the answer is 5,000. Alright, so 5,474. Okay, 5,474. Okay. Grams. Okay, so 5,474 grams of lithium. Alright, so lithium carbonate that will be produced. Okay, so why the large number? Okay, so if you are wondering why the large number, because your volume that you have right here is very large. Okay, the volume that you have here in the first place is very large. So it means that, okay, so it means that this particular, okay, so this particular answer that we have right here is somehow correct, because if we have a large volume, then therefore the product is expected to have a large quantity as well. Okay, so this was the 5th problem for the ideal gas law. So again, before you solve this kind of problem that we have right here, okay, so before you solve this kind of problem, first balance the equation. Okay, after you balance the equation, that's the time that you will perform all your calculations regarding your ideal gas law. Now, before you calculate the ideal gas law, or before you calculate your variables, make sure that the variables correspond to the correct units, okay, to the converted units following the R of your ideal gas law. All right, so this is the answer for this question: 5,474 grams of lithium carbonate that will be produced in the process. Okay, so that is the 5th problem for the ideal gas. And that ends up our topic for this video lesson about the ideal gas law. I hope you'll be able to get value on this topic we discussed today. And if so, don't forget to like this video. If you have questions and suggestions, write them down in the comment section below this video. It will help me a lot in the algorithm for my YouTube channel. And most importantly, don't forget to subscribe to my channel and hit the notification bell for you to be updated for more science video lessons like this in the future. I'll see you next time, everyone. Enjoy learning and practice always. Stay safe and peace out. Okay?